Hello and welcome. So for those of you that don't know me, my name is Mike and this video is another installment in the rather unimaginatively titled series that I'm currently working on, which is Philosophy 101. And the purpose of this series is to provide people with an introduction to philosophy that allows them to not only understand what philosophers are talking about, but also to actively engage in the act of philosophy. And this video is part of a subsection of that series in which we are examining argumentation and reason and logic and critical thinking. So in the last video we explored the structure of arguments, focusing on premises, conclusions, validity, and soundness. So today we're going to take that a step further and go into the realms of formal logic, which uses precise tools to analyze arguments mathematically. We'll learn how to work with logical operators and truth tables to evaluate deductive arguments. So for the agenda today, or on the agenda today, there are sort of four parts to it. So part one is, what is formal logic? We're going to explore this question. We're going to attempt to unwrap exactly what formal logic is and why we should use it. And then once we've done that, we can then move on to part two, where we're going to look at the logical operators and their meanings, and how that translates when we are when we actually want to use them. So from there, we're going to go and look at truth tables in part three. So truth tables are a wonderful tool that we use to analyze and evaluate arguments. And then from there, we're going to look at some examples, some practice examples that we're going to work through. So what is formal logic? Formal logic focuses on the structure of arguments rather than its content, and it uses symbols and rules to represent and analyze reasoning, ensuring clarity and precision. So why would we even want to use formal logic? What's the benefit? What's the point? Well, there's a couple of things, three things that come to mind. First is to evaluate arguments systematically. The second is to identify logical relationships between statements. And the third is to avoid ambiguity in reasoning. So let's go back to that first one, to evaluate arguments systematically. Formal logic provides a rigorous framework for analysing arguments and ensuring their validity. By focusing on the structure of an argument rather than its content, formal logic helps determine whether the conclusion necessarily follows from the premises. This systematic approach eliminates guesswork, which allows philosophers and scientists and debaters and thinkers of all stripes to test the strength of their reasoning. For example, if someone argues if it rains, the ground will be wet, it is raining, therefore the ground is wet, formal logic identifies this as a valid argument through the rule of modus ponens. That's a bit of a mouthful. Systematic evaluation ensures that arguments are not only persuasive but also logically sound, which makes it an invaluable tool for critically thinking and problem solving. So point two of the 3 points that I raised was to identify logical relationships between statements. Understanding how different statements relate to each other is crucial for constructing coherent arguments and uncovering hidden implications. Formal logic identifies relationships like equivalence, contradiction, and entailment, enabling a deeper understanding of how ideas interact. For instance, in ethics, a philosopher might argue if killing is wrong, then capital punishment is wrong. Formal logic helps trace the relationship between principles to determine whether they are consistent and whether they lead to contradictions. By mapping out these relationships clearly, formal logic supports the development of robust theories and arguments that hold up under scrutiny. And the final of those three was to avoid ambiguity in reasoning. Natural language, as I'm sure you're aware, is often imprecise, which leads to misunderstandings or weak arguments. Formal logic replaces vague expressions with well-defined symbols and structures, ensuring clarity in reasoning. As an example, the statement, "if you study, you might pass the test," is ambiguous because the word might is open to interpretation. In formal logic, this could be expressed as a conditional or a probabilistic relationship, depending on the intended meaning. By eliminating ambiguity, formal logic ensures that arguments are interpreted as intended, fostering precise communication and robust intellectual discourse. So this clarity is especially important in fields like law and philosophy and AI and many more, where ambiguity can have significant consequences. Consider, if you will, the following two arguments. Argument 1, if it rains, the ground will be wet. Argument 2, if it rains, my umbrella will be red. So these two arguments actually both have the same structure. If A, then B. Formal logic lets us to analyze this structure without worrying about specific content. So at this point, I have a question for you. And it's a question I want you to answer in the comments. So once I have read the question, pause the video and go and answer in the comments. I'm going to follow up with my own answer in a moment. So after I've, asked you the question, pause the video so that your own thoughts aren't sort of taken over by mine, essentially. So the question is, why might a symbolic representation of arguments be more helpful than natural language in some cases? So that question again is, why might a symbolic representation of arguments be more helpful than natural language in some cases? So go ahead and pause the video and go and answer that, and then upon your return, I will give you my answer. So did you pause the video? And did you answer? Well, I hope so, but we will soon find out, right? So a symbolic representation of arguments can indeed be more helpful than natural language in some cases for several reasons. So I've got 6 listed for you, but there are more. But these are the 6 that came to mind when I sat and had to think about this question. So we'll start with clarity and precision. Symbolic logic eliminates ambiguity and vagueness that is often present in natural language. Words can have multiple meanings or connotations, but symbols in formal logic have clearly defined interpretations, which makes arguments easier to analyze. And the second reason that I thought of why a symbolic representation of arguments might be more helpful than natural language is the universality of the language that we're using in formal logic. So symbolic logic provides a standardized way to represent arguments independent of any particular natural language. And this universality makes it easier for people with different linguistic backgrounds to communicate and reason about logical structures. The third reason is that in natural language, complex arguments with multiple premises and conclusions can become somewhat cumbersome to express and follow. Symbols and formal notation allow for concisely representing even highly intricate arguments, making them easier to handle and manipulate. Our fourth reason is that it is to do with formal analysis. Symbolic representation allows the use of formal rules of inference, proof techniques, and automated tools like theorem provers. And this formal framework is critical for ensuring the validity of arguments and conducting logical analysis rigorously. Now, a fifth reason has to do with the focus on structure. So symbolic logic it abstracts away the specific content of an argument, focusing instead on its structure. And this makes it easier to identify logical forms, common patterns, and potential fallacies, which the content in natural language very often obscures. And the final point that I'm going to make here before we move on is to do with consistency checking. Symbolic logic allows for systematic methods to check for consistency, validity, and equivalence of arguments. And this is really quite difficult to assess accurately in natural language due to its complexity and variability. So in short, symbolic representations are particularly valuable in contexts where precision, universality, and formal analysis are necessary, such as mathematics, computer science, philosophy, critical reasoning, and actually like everyday problem solving. So now that we have spent some time digging into exactly what formal logic is, we can start to think about the logical operators and their meanings. So in formal logic, we use operators to represent relationships between statements, and these operators are like the grammar of logical reasoning. So I do have some slides for this, so bear with me a moment. So, as you can see on the screen, we have 4 different logical operators that we're going to discuss. We have and, which is also known as a conjunction. We have or, which is also known as a disjunction. We have not, which is known as a negation. And we have if then, which is known as a conditional. So with the conjunction, with the and, it's true if both statements are true. So the example that you can see on the screen is, I'll go for a walk if it's sunny and I have the time. So the I'll go for a walk part is true if it's true that it's sunny and it's true that you have time. They both have to be true for that overall statement to be true. And then we have or the disjunction. So in this case, it's true if at least one statement is true. And as you can see in the example, we have, I'll go for a walk if it's sunny or I have the time. So only one of those needs to be true. Either it's sunny or I have the time. And if one of those is true, then the overall statement is true. And then we have the negation, or the not, which negates the statement. So if we had a statement, it's raining, a negation of that would be it's not raining. And then we have the conditional, the if-then statement. So it's true unless the first statement is true and the second is false. So the conditional is true unless the first statement is true and the second is false. And the example of that is, if it rains, the ground will be wet. So that will be true. If it rains and the ground is indeed wet, then that's true, right? It's fairly simple, fairly simple stuff. It does, the way people talk about this sometimes as if it's complicated, and it's not. It's really not. And it isn't actually that far removed from the way that we do speak in natural language, but obviously it's much more precise than natural language. So let's have a look at some of these operators in practice. So we have, it is sunny and it is warm. So statement one, it's sunny and it's warm. So it's true if it's both sunny and it's warm. And statement two, we have, it is sunny or it is raining. So the overall statement is true if one of those, i.e. it's sunny or it's raining, if one of those is true, then the overall statement is true. Then we have the negation. So it is raining, or the negation of that is it's not raining. So it's true if it's not raining. So if that statement, it is raining, it is negated, then it's true if it's not raining. And then we have, if it rains, then the ground will be wet, which is true unless it rains and the ground is dry. So that's simple enough, right? So at this point, it would be a good idea to jump into the comments and try and write a sentence that uses one of these operators and actually translate it into symbols. And if you can't figure out how to type those symbols, you can do it on a bit of paper, back of an envelope. It doesn't really matter. What matters is that you have a go at sort of practicing using them so that they become ingrained. So go and do that now and pause the video while you do that. And when you come back, we can have a look at truth tables. So pause the video and I will see you upon your return. So, did you pause the video? Well, I hope so. And I look forward to reading your sentences. So we've just looked at the operators that we use, the logical operators, and from there the natural sort of progression from that point is to examine truth tables. And truth tables are tools that we use to evaluate the truth value of logical statements. They show how the truth or falsity of individual components affects the overall statement. So here we have a truth table, and it's a really simple one. So we have a column for A, a column for B, and a column for A and B. So the statement, if A is true, then B and B is true, then this statement A and B is true. But if A is true and B is false, then A and B is false. And so on. So you can see from this table that's on the slide right now that in order for the statement A and B to be true, both A and B need to be true. And you can see when, so that top row, you have true, true, true. So A is true, B is true, therefore A and B is true. But every other row, A and B is false. So why is that? Well, let's look at the second row. So A is true and B is false. Therefore, A and B can't be true because only A is true and B is not. It's false. And then in the next row, we have essentially the opposite. So this time, A is false and B is true. But the result is still the same. The statement A and B is still false. And finally, we have A is false and B is false. And again, this results in the statement A and B equating to false. So this table essentially tells us that A and B is only true when both A and B are true. So from here, let's try and make, a table for a more complex statement. So A or not B is our statement that we're evaluating. So as you can see from the table, we have A is true, B is true, not B is false. Therefore, this statement, A or not B, is true. And then in the second row, we have A is true, B is false, not B is true. And this means that the statement A or not B is false, is true rather. And then we have the third row where A is false and B is true and not B is false, which means the statement A or not B is false. And then finally we have A is false in this bottom row, this fourth row. We have A is false, B is false, but not B is true. Therefore, the statement A or not B is true. So hopefully that made sense. But the truth table makes it really easy to evaluate these statements for what they are, and do so in a way that cuts through the noise and the ambiguity of natural language, and it doesn't worry about the actual content. It's purely about the structure. So these truth tables enable us to access that structure in a way that's it's fast, it's efficient, and it's also, for us human beings, it's visually speaking, it's we're able to look at it and understand it without any great explanation. So we're going to get into some examples in a minute, but I do have an activity for you to do, and this ideally pause the video and grab a pen and paper, or do it in the comments, whatever works for you. But what I want you to do is to create a truth table for the statement if A then B. So create a truth table for the statement if A then B. And post it in the comments, and I look forward to seeing those. But at the very least, grab a pen and paper and get scribbling. So write a truth table for if A, then B. So you need a column for A, you need a column for B, and you need a column for the overall conditional, the if A, then B. So 3 columns. So go ahead and do that, and then when you come back, we will look at some examples and get really stuck into it. So, did you pause the video and create that truth table? I certainly hope so. So let's move on now and start getting into some practice examples, right? So our first example is going to be focusing on validity. So consider this argument. Premise 1, if it's raining, the ground is wet. If R, then G. Premise 2, it's raining. Conclusion, the ground is wet. So let me say that again. So premise 1, if it's raining, the ground is wet. If R, then G. Premise 2, it's raining, which is R. Conclusion, the ground is wet. G. So is this argument valid? Well, we can actually use a truth table to confirm this. So let's go ahead and do that. If R, then G. So this is the truth table for that argument, which is then broken down or symbolically represented as if R, then G. So let's try and explain it. So when R is true and G is true, the statement if R then G is true because G occurs when R occurs. And if R is true and G is false, the statement if R then G is false because G does not occur when R occurs. When R is false, regardless of G, the statement if R then G is true. In formal logic, a conditional statement with a false antecedent, in this case R, is considered true because it does not contradict the if-then condition. And that's important. So let me say that again. In formal logic, a conditional statement with a false antecedent, which in this case is represented by R, i.e. it's going to rain. So a conditional statement with a false antecedent, R, is considered true because it does not contradict the if-then condition. So when R is true and G is false, the conditional if R then G is false. Since this doesn't match our premises, the argument is valid when the premises are true. So let's for our second example, let's think about logical equivalence. So are these two statements logically equivalent? So statement 1 is a negation. So we have A and B, but the whole thing is wrapped in brackets and is negated. So much like in mathematics, we have to treat the A and B as a singular thing, and that negation negates the whole thing, if that makes sense. So are these statements logically equivalent? So not A and B. And yeah, so sorry, I totally lost my place then in my notes. So yeah, the first statement is not A and B. So the A and B, the whole thing is negated. And the second statement, not A or not B. So are these these statements, are they logically equivalent? So we're going to use a truth table to find out. And before I go ahead and sort of share that with you, I want you to pause the video and have a go at this yourself. So set up a truth table. So you want you want to find out if these statements are logically equivalent. So pause the video and have a go at that, and then when you come back, we will dig into it. So, did you pause the video and have a go at that? Did you have a go at using a truth table to find out whether the two statements on the screen are logically equivalent? If you did, brilliant. And if you didn't, don't panic, don't worry, there's an explanation coming. So this is, that you can see on the screen right now, this is a truth table that we can use to figure out whether these two statements are logically equivalent. And as you can see, we have a column for A, a column for P, a column for A, a column for B, a column for A and B, and then we have a column for the negation of A and B, and then we have a column for not A, a column for not B, and a column for not A or not B. So are these statements logically equivalent? So I'm not going to go through reading out the true, false stuff to you. Let's think about this. So when let's try that again. If you look at every row, the truth value of not A and B matches the truth value of not A or not B. So if you look in the first row, A is true, B is true, A and B is true, and not A and B is false. So the negation of A and B is false. And we also have not A is false, not B is false. Therefore, not A or not B is false. So as you can see, the not A or not B has the same result, i.e. it's false, as the not A and B. And the same is true for every arrangement of true and false that we've got in there. So if A is true and B is false, then A and B is false. Therefore, not A and B is true. And we have not A is false, not B is true. Therefore, not A or not B is true. And we also have in the third row, we have A is false, B is true. Therefore, A and B is false. And the negation of A and B is true. Which also means that not A is true and not B is false. Therefore, not A or not B is true. And in the bottom row, we have A is false and B is false. Therefore, A and B is false. Therefore, not A and B, i.e. the negation of A and B, is true. And also, therefore, not A is true and not B is true. Therefore, not A or not B is true. So as we can see, the values for the truth value of the not A and B, and it matches completely with the truth value of not A or not B. So that was all a bit of a mouthful, I must say, but hopefully that truth table being, in front of you right now makes it much easier to understand and get to grips with. And these truth tables are wonderful tools because, as you just heard, when someone says all of that stuff, it's just like noise. It's word salad. It's like, what does that even mean? But when you see it laid out in that table, you can look at it and it's like, oh, now that makes sense. So these truth tables are a fantastic tool. They really are incredibly helpful. So let's get rid of this slideshow. That wasn't the right button. Sorry. Oh, there we go. So as you have now discovered, formal logic allows us to analyze arguments with precision. By using operators and truth tables, we can determine the validity of arguments and the logical relationships between statements. So as an exercise for you to do before we part ways, or as we part ways, should I say, I want you to have a think about and then do. I want you to write a short paragraph or two answering this question. What do you think let me try that again. How do you think truth tables can be useful in real-world decision-making or debates? So that question was, how do you think truth tables can be useful in real-life decision-making or debates? So I want you to put your responses in the comments and, write a paragraph or two or go wild. It's fine. I will read them all. So I certainly endeavour to. So jump in the comments with all of that, and I very much look forward to reading your responses. Not only will it be interesting for me to read, but it will also show me whether I've explained all of this stuff very well or not. So if you do that, you obviously benefit from articulating your thoughts and solidifying your newfound knowledge and using it, and I benefit because then I know that if I'm doing a good enough job of explaining it, because I normally do this with an audience, so it's there's like real-time reactions that I can gauge that will enable me to see whether I'm sort of explaining things well or not. But in this format, i.e. recording for YouTube, there is no audience, so therefore there is no feedback for me. So it's unclear whether I'm explaining it in a way that's actually landing. So your answers to this question, how do you think truth tables can be useful in real life decision making or debates, is one of the ways that I can use to figure out whether I'm doing a good enough job at helping you in your learning journey. And so that's all for formal logic. So I don't want to weigh you down with too much, because there's quite a lot in there already that you can start to think about and use. So in the next video, we're going to move on to identifying logical fallacies, which are like common errors in reasoning that weaken arguments. And this logical fallacies is actually my of all the sort of topics we've got to cover in this series, this is my favorite one to talk about. So I really look forward to seeing you on that one. And before I go, as you've got this far in the video, if you found this helpful and useful or interesting or whatever, then I would really appreciate if you could like the video and subscribe to the channel. This will mean that YouTube will show you more of my stuff, which is fantastic for both you and for me. But more importantly, it will let YouTube know that actually you're not just interested in me, you are interested in the subject at hand, i.e. philosophy, and it will start to show you other people talking about philosophy and its associated subtopics, which will help you to widen your net, as it were, to broaden your horizons and not be too caught up in any sort of singular interpretation of these ideas. So that would be of great benefit to you and your critical thinking skills. So if you could do that, that would be fantastic. But if not, there's totally no pressure. It's fine. As I say, I hope you enjoyed today's video. I hope you found it interesting. And I very much look forward to seeing you on the next one where, as I already said, we're going to be looking at some logical fallacies and, you know, how we can spot those in the wild. So I hope to see you there. Thank you very much for your time, and goodbye.